page rank hits and so on. Now I'm also adding some exercises on similarity clustering. So today I would like to start with one possible exercise, for example this one, and we could see two things with this exercise. First, we can solve it at the blackboard, and second, we can try to check the answers by writing a small program that computes the answer. So the exercise provides 5 different documents. Each, of course, is very small, so that we can handle it without a computer. The idea is that we want to cluster these documents based on their contents. So, the idea, okay, you see here, the system that we want to use only considers these grammar categories, so nouns, adjectives, pronouns, adverbs, and verbs. So, first thing you're asked to do is remove all words that are not considered by the system. So you're asked to reduce your these documents to a set of words in these grammatical categories. So all forms of nouns and adjectives must be converted to singular. All verbs must be converted to the infinitive tense, of course, without removing the initial two. Remove all punctuation marks, translate all letters to uppercase. Conjunctions, prepositions, articles, and exclamations are discarded. And multiple occurrences of the same term within the document are not counted. So we are actually requiring to do a small handwork of stop word removal, stemming, and final creation of a back of words model. Why back of words model? Because in fact we are not considering the number of occurrences of each word. So here you have an example of what must be done. Okay. In this case, the phrase "Hey" is not too late to solve these exercises. "Hey" is an exclamation, so it must be removed. "It is" pronoun and verb must be converted to their fundamental form. "Not" is an adverb. "To" another adverb. "Late" again an adverb. "To solve" solve. "These" converted to the singular form. "This" exercises to exercise. Okay, so this is the set of words corresponding to this document. The questions are the following. Okay, actually the first question refers to a TF-IDF vector space, but in the other questions actually consider the back of words model. So the first question is, what is the minimum dimension of the TF-IDF vector space for this collection of documents? Of course, there is a solution below. I would ask you not to look at it and to reason about this, okay? And then the second question is, okay, you have 5 documents, so you can compute all pairwise Jacquard coefficients. Then 8.3, using this similarity measure, try to apply the agglomerative clustering procedure, the procedure that we have seen yesterday. Of course, you should use a similarity measure, the Jacquard coefficients, and as a similarity measure between two sets, consider the highest similarity, so the maximum of all pairwise similarities between the two sets. Okay, so maybe I can give you a few minutes to reason about this, or maybe you already have some answers. So, for example, is question 8.1 clear? Or you have some doubts about its meaning? And if the question is clear, what is the answer?
Could you explain this, please?
Yes. Okay. So, in the first point, we want to represent all documents in a vector space, where the vector space contains one number, one coordinate for every term in the document space. So the idea is that you have to see how many terms, excluding stop words, are contained in this document corpus. And these are actually the dimensions of the vector representation of the document. It is that if you have a document that contains terms A, B, and C, and a second document that contains terms B, C, and D. If you want to represent these two documents in a single vector space, what you want to do is actually to consider the whole set of terms contained in all the documents. In this case, if you have two documents, look at this and, okay, the set of terms is A, B, C, and D. Then, documents D1 can be represented as a vector that contains as elements the number of occurrences of each of these terms. So for example, D1 can be represented by vector 1, 1, 1, 0, meaning that it contains one occurrence of A, one occurrence of B, one occurrence of C, and no occurrences of D. Okay. So the idea of the TF-IDF vector model is that you create a vector space where you represent each document by some vector of numbers, each number representing the importance of a term within that document.
But why is that minimum dimension? Because it's actually only one dimension. How we can represent it?
Sorry?
It's the only one dimension. Why it's a minimum dimension?
Okay. Of course. Yes, in that case I could have removed minimum. Actually, it doesn't hurt to add dimensions. I mean, if you assume that, okay, if this is the complete corpus, you have no reason of adding more dimensions than necessary. Yeah, so you're right. I just wanted to highlight that I wanted to discard all unnecessary terms. Okay, so in this case, for example, you can see how many words D1 contains. And D1 contains, okay, first the verb, be, or is discarded, because it's a conjunction, not remains. Then the verb be is repeated, but we are not considering multiplicity, so be can remain just once. Then the word this. Then again the verb to be is. An article can discard it, and finally the word question. So document D1 is actually the set of terms be, not this, the question. Okay. The second document, same approach. the pronoun I, the verb have, the article a is discarded, the word, the noun here, the preposition of is discarded, problem, so problems in the singular form, for is again a preposition and is discarded, you, to solve, and the adverb today. Document D3, the pronoun it, the verb be, the adjective long, the noun way, preposition to is discarded, the noun temporary, then again it, be, long, way, so I discard them because they already appear, and finally the verb go. Document D4. I have, actually I've been, so actually this is the verb be, okay. Walk. Well, actually this depends. I've been walking actually is a form of the verb to walk, so maybe I could also have written only I and walk. It depends on how strong is your grammatical analysis program. So, and it depends on how you interpret the rules of English. So let's say I've been walking can be actually just a form of the verb walk. Long, wait. In any case, the verb to be appears later, so it can be there. Then the adverb here and the adverb there. Of course, okay, sorry?
You is not considered here?
You're right. We also have you. Anyway, I don't require you to know precisely the English grammar because I don't. So, if if you find an exercise of this kind in the written exam and you have any doubt, you can either ask me or decide with your interpretation and clarify it. So I accept different interpretations if there are any doubts. Okay. A few questions will be actually open questions where you can you are actually expected to give different answers. So in some cases I only want to see if you are able to discuss the topic. Okay. Finally, document D5, I, B, not able, question, this, and order. Okay, so we have transformed the 5 documents into 5 bags of words. Now, let's see what it means with regards to the first question. Actually, all the first question requires us is to count how many different words there are in these 5 sets. So actually to take the cardinality of the union and provide that number. We can list them, okay? So we have B, no, this question, I have pair problem, you solve today, it, B is already here, long, wait, Hierarchical. Go. Yeah. I is already there, B is already there, walk. Long, way, you, here. Today is already there. I, B, not able. Question. This, then order. Okay, so we have okay, we simply need a 20-dimensional space to represent these documents. So, for example, D1 would be the set 1, 1, 1, 1, and then all zeros, though not the set, the vector, okay, in R20. Okay, so in any case, the answer to the first question is simply 20. Give or take 1 or 2, depending on how we interpret some words. Now, let's see the second question. Okay, is everything okay here? Now, the second question asks to compute all Jacquard coefficients for all pairs of documents. Okay, we can do it in many different ways. Okay, let's do this. Okay, so we want to compute the Jacquard distance between D1 and the other documents. So the first thing we can do is, first of all, write down the length of all documents. Because we need it to compute the Jacquard coefficient. So this is 4, this is 7, this is 6, D4 is 8, and D5 is 7. Okay, then to compute the Jacquard coefficient, we just count the number of common terms between two documents, and then we divide it by the sum of the two lengths minus their common terms. So for example, okay, the Jacquard coefficient between D1 and D2 is very easy. There are no common terms. So it must be 0. The Jacquard coefficient between D1 and D3. Well, of course, things would be a little easier if I had written the terms in alphabetical order, but it takes time, so maybe it's easier this way. So we have B, and nothing else. So the intersection is 1, and the union is 6 plus 4, 10, minus 1, 9. We can keep it in fractional form. It's easier than writing decimals.
Could you repeat once again the 9, how we get it?
Yes, so the Jacquard coefficient between D1 and D3, okay, which is the size of the intersection divided by the size of the union. Actually, instead of writing the size of the union, we can write the size of D1 plus the size of D2 minus the size of the intersection. So the intersection is 1 because there is only one term in common, B. Okay, apart from B, there are no other common terms between D1 and D3. Sorry, this was D3, of course. Then the length of D1 is 4, the length of D3 is 6. So 1 divided by 9. And again, we do the same for D1 and D4, where, okay, apparently they only share the word B, again. So the intersection is 1, the union is 4 plus 8 minus 1, so it's 1 over 11. And between D1 and D5, we have B, not, and this question and this. Yes, okay, so we have 4 terms in common. Actually, D1 is a subset of D5 from the point of view of the bag of words model. Of course, here, for example, you might object that, you see, in this case, for example, the word question, here is a noun. Okay, it was to be or not to be, this is the question. Okay, here question is a noun, while here to question is a verb. So actually you could have decided, and there are some text analysis tools that tag every word with its grammatical sense. So the two words question, in this case, would be tagged, one with the noun tag and the other with the verb tag. So they would be kept separate. They would actually be two different words. In this case, to simplify things, I assume that we only looked at the word itself without tagging it with any meaning, so the two words question are actually the same. In this case, so the intersection is 4, and the union is 7. Actually, the union of the 1 and the 5 is exactly the 5, so the 1 is a subset. Okay, we have done more or less half of the work now, because, of course, the Hierarchical coefficient is symmetric, so we don't need to recompute the Hierarchical coefficient between the 1 and the 2. So we only need to compute the coefficient of the 2 with the 3, the 4, and the 5. So here it's looks a lot 0 to me. Maybe it is. Yes. Okay, there are no common terms between the 2 and the 3. D2 and D4. You, and today I see 3 common terms. Yes. 3 common terms out of 7 plus 8, 15 minus 3, 12. So 3 over 12. Okay, that's just rewrite it as 1/4. Again, the 2 and the 5. And nothing else. So it is 1 over 13. At least it seems to me. Yes. Perfect. Let's complete the table. So between D3 and D4 we have B, long, way, nothing else. So 3 out of 11. 8 plus 6 minus 3. Between D3 and D5, B, and apparently nothing else. So it's 6 plus 7 minus 1, 1 over 12. And finally, the similarity between D4 and D5, I, B, and nothing else, so it's 2 out of 8 plus 7 minus 2, so out of 13. So it should be similar to this. Okay, so assume that these are the correct numbers. now we want to run our agglomerative clustering procedure. To do it, okay, let's see. We need to repeat this process many times. We find the two most similar objects in this table, and then we join them together. What are the two most similar objects here? We just look at the highest Hierarchical coefficient. In this case, this is more than 1/2. So for sure it's the largest one. So as a first step, we are going to merge together D1 and D5. Okay, merging together D1 and D5, and as long as we do it, we can also maintain a dendrogram, which is asked as the fourth question. So we can just draw D1 and D5 and say that we join them at a similarity level of 4/7. Okay, this is the similarity at which we can group them together. Now, I've written this one too large, then I don't know where to put the new table. Let's see. Now, I'm not interested in this table anymore. This table shows me the similarity between every item and every other item. But what I want actually now is a table where D1 and D5 are merged together. So I can rewrite the table by only considering the similarity between objects D1, D5, but I don't want to write it here because I need space for the dendrogram. Let's do this way. So I'll just draw the dendrogram horizontally, so it will take less space. Here I want the table that shows the similarity between the set D1, D5 and all the other sets. You see, I just have to look at this table and take the right numbers out of it. The similarity between D1, D5 and D2 is the maximum of the similarities between D1, D2 and D5, D2. Because the exercise asks to consider the maximum similarity, pairwise similarity between the elements. So just look at the similarities of D1 and D5 with respect to D2. D1, D2 is 0, and D5, D2 is 1/13. So actually the number I'm interested in is 1/13. I discard 0. Okay, so in general here, the similarity between two sets, D1 and D2, is taken as the maximum for D1 in D1 and D2 in D2 of the similarity between D1 and D2. Okay, this is the definition of set similarity that I'm considering, that the exercise is asking for. The similarity between D1, D5, and D3 is the maximum between 1 over 9 and 1 over 12, so it's 1 over 9. And finally, the similarity between D1 and D4 is 1 over 11. And the similarity between D5 and D4 is 2 over 13. Okay, the largest is, of course, 2 over 13. And let's just rewrite the remaining part. So we need to copy down the similarity between D2 and D3, which is 0. D2 and D4 is 1/4. And then D3, D4 is 3 over 11. Okay. This is the new table after merging D1 and D5. Okay, in summation, we have two ways to proceed. Either we keep looking at this table and and to compute set similarity, we look at the largest between some numbers, or we rewrite the table by removing the unnecessary information at every step. So now I'm proposing this so that I can get rid of this table, which is not needed anymore. Of course, I could have made some errors here, so the numbers on the exercise are actually the correct ones. Then we repeat. What is the next, the largest number here? 1/4. Let's see. No, it's 311. Yes. Okay, the largest number here is 3 over 11, which is larger than 3 over 12, of course. So the next merge will be between D3 and D4 at the similarity level of 3 over 11. So now we can rewrite the table by taking the previous table and merging together D3 and D4. So actually the similarity between D1, D5 and D2 is the same as before, 1 over 13. The similarity between D1, D5 and D3, D4 is the largest between the two similarities of D3 and D4. Okay, so in this case, it's 2 13ths, which is larger than 1/9. Then the only other similarity that we need, given that D3 has been absorbed with D4 and does not exist anymore, is the similarity between D2 and D3, D4. Okay. Similarity between D2 and D3 is 0. Similarity between D2 and D4 is 1/4. So we have 1/4. Again, the largest similarity here is 1/4. So we are joining D2 with D3, D4 at a similarity level of 4. So now we have just 2 clusters, and the next step will be, of course, joining everything together. Let's see at what similarity level we are joining them together. So we join D2 with D3, D4. So the only similarity that remains to be computed is the similarity between D1, D5 and D2, D3, D4, which is the largest similarity between D1, D5 and D2 and D1, D5 and D3, D4. So the maximum of these two numbers, which is 2 over 13. And this is the final merge, where we join the cluster D2, D3, D4 and the cluster D1, D5 at a similarity level of 2 over 13. And from this point on, we only have one cluster. The last table before joining them together. Of course, I repeat, this is not the only way of performing the agglomerative clustering procedure. The only, of course, every procedure you choose, every set of steps you choose, you should get to the same result, okay? Either by reducing the table or by looking at the maxima at the time. Okay, anyway, what I am proposing now is, let's try to write a short script to try to solve the exercise. So, what I propose is, let's start from this document already tokenized and transformed into bags of words. So we don't need to consider grammar, stemming, and so on. Let's start from that and try to compute the algorithm. So, okay, so Okay, let's say I'm calling the file exercise8.py. Okay. And so what we want to do is define those 5 documents. So let's say we can simply declare a list of strings, each string being one of those documents. So be not this question. Then the next string will be I have prepared problem you solve today. The next is it the long way literally go. Next, I be walk long way you here today. And finally, I be not able question this folder. Okay, so we have these 5 documents. First thing we can do with this document is, with this set of documents, is, okay, we want to transform them into bags of words. So the easiest way to do it is to define a set, let's say S. So we can transform each of these strings into the corresponding set for D in okay, no. Let's say for every string or document, let's say D in uppercase D, we want to take D, split it according to space character, so we can actually, okay, take every document in D. We create a list of tokens separated by spaces, and then each of these lists is converted into a set so that we can play things as in intersection, union, and so on with them. So in fact, if I try to print S, okay, S is a list of sets where each set is the corresponding set of words. Okay, so this is the bag of words representation of the first document. This is the bag of words representation of the second document, and so on. Okay. Now, let's write a simple function to compute the Jacquard coefficient between 2 documents represented as sets. So I want to define the Jacquard coefficient between 2 sets S1 and S2. Okay, last time I considered the Hierarchical coefficient between two sorted lists. But in fact, if you use sets, it's much easier because you just need to consider the number of elements of each of the two sets. And the number of elements of the intersection, where the intersection between sets is rather straightforward. Maybe there are also other ways to compute to other notations, but and then we just need to return so n divided by, okay, actually we need to convert them into floats, just one, and the second is n1 plus n2 minus. Okay, let's see if it works. So, for example, let's create a table of all Hierarchical coefficients. I want to compute Hierarchical of S1 and S2 for S1 in S and S2 in S. Of course, in this way, we are going to see only an indifferentiated list of numbers. So it's rather difficult to interpret it. What we can do is make it create a table. So we just create a list of lists for S1 and S2 varying within the set S. And of course, rather than printing J, we can, well, just to see it in a better format. Let's write it as in a square matrix form. So maybe we can say L. Okay, so I separately write the lines of the matrix. Let's see if it works. Okay, so these are all the Hierarchical coefficients between every document and every document. So of course we will have 1 along the diagonal, because the similarity between the document and itself is 1. And then we should have numbers that are similar to the ones that I erased before. So maybe if you want later you will check them with respect to your notes or to the solution of the exercise. So we created all Jacquard coefficients between all pairs of documents. Now we want to run the clustering procedure. Okay, we can. Okay, first of all, let's call C the set of clusters. You know that we start with a set of clusters where every cluster is a singleton. So the first thing we do is define C as this set of singletons. Remember that I had called S the set of bags of words. So I just need to take every element in S and enclose it into, let's say, we can use maybe a set. Yes. Okay, so S are the bags of words. I take them and enclose each of them into its own singleton set. Now I have to repeat some conglomerating procedure as long as C has more than one set. Okay? So I stop when I merge all sets together. Every time I want to find the two sets that have the highest Jacquard similarity. We can use this matrix, but okay, let's do it in a straightforward way. Maybe not optimal, but straightforward. Let's define another Jacquard similarity, let's call it Jacquard 2, that works between, not between two bags of words, but between two sets of bags of words. So two clusters, let's say C1 and C2. And in this case, I just want to compute all pairwise similarities between elements in C1 and elements in C2. So just create the list of all Jacquard similarity between S1 and S2 for S1 in C1 and for S2 in C2. Then I want to take the maximum of this list and just return it. Okay, so now okay, so Jacquard works between two elements, and Jacquard 2 works between two sets, two clusters. So now, every time, we just need to find the maximum similarity between two elements of C, two clusters of C, and merge them. So, for example, just we look at the maximum in a straightforward way by scanning all elements in C. Let's say I want to look to all elements but the last one, and okay, I want I and j to be indexes of C, so that I and j scan all pairs in C, all distinct pairs in C. Okay. So I varies on all elements of C apart the last one, and j starts from I plus 1 and scans all the remaining elements of C. So I just need to compute the similarity using the Jacquard 2 function between element I of C and element J of C. And if S is greater than the maximum that I am storing in M, which I initialized at 0, just remember the new largest similarity, and of course let's store the position of the maximum into two variables, let's say Mi and Mj. Okay, so after this loop, I have that the largest similarity happens between elements with index Mi and Mj, and its value is M. So we can write it out. Largest similarity between the largest similarity is this number between these two indices, and the similarity is stored in M, and the two indices are Mi and Mj. Now we have to remove the two sets with index Mi and Mj from C and add their union to C. So let's just pop the element of index mi from C, and we store it in the variable ci, for example. We do the same with the jth set, so cj actually, since I already popped the mi, actually the element which was at index mj is now at index mj minus 1. And then I just append ci union cj to my set C. Okay, so this is actually the Python implementation of the pseudocode that we saw yesterday on the blackboard. What next? Of course, I want to see the contents of the of C at every step. So let's start by just printing it.
It should be out of cycle, the print.
No, I want to print it at every iteration,
okay.
So you can see it. Actually, I'm afraid that we won't see that much because, well, apart for errors, of course. Okay. Oh. Okay, first thing, I cannot put okay. Okay, so it doesn't let me take sets out of this. But I want to put this set. Okay, let me do this. S is just a list of lists, and I convert them into sets just when I need, well, actually not here, but of course, this is not really optimal. What I want to do. Oh. Okay. Anybody here with a good understanding of list comprehension in Python? So let me remove everything that I don't need. Okay, the problem is here. So, okay, then I can let C be a list of lists and not of sets. In fact, this list will always be disjoint. So instead of union, here I can simply add two lists. Okay, it works, but it's rather difficult to understand. So, let me also print C at the beginning. Okay, so the point is where, so to understand this, you need to look at where the brackets are. So, starting from here, this is the initial version of C. Every set is enclosed in its own list. In the second step, but of course we will need to find a better way to see it. Two steps, meaning documents 0 and 4, because here we are, indices are 0 based, so they are documents D1 and D5 have been joined together in the same cluster. And you see here the highlighted part. Let me find a better way to represent this. So let us define a few functions to print it out in a reasonable way. So maybe a function that prints out a bag of words. So just for every word in our bag of words, so we write out all words separated by spaces and nothing else. So actually, it's easier this way. Let me see if it works. For example, by printing type of word now. The first. Okay. So with this, we write a bag of words. So if we have our clustering C and we want to print it, just just write plus the 0 and then for every document in our cluster okay, actually we don't need the print bag of words function. You can just use it here. Okay, okay, let's see if this works. Okay, I just forgot to increase n. Maybe here separator. So let's see how it works. Okay, so maybe later we can see the code again. Anyway, so we are starting with a set where every cluster only contains one document. Then clusters 0 and 4, which have a similarity larger than 1/2, we've seen it was 4/7, are joined together. So we remain with 3 clusters where the last cluster is the previous clusters 0 and 4. Here. Next, these 2 clusters are merged together because they have this similarity, and we end up with these 3 clusters. and so on. So next time clusters 0 and 2 are merged together with similarity 1/4, and we end up with these two clusters. And finally, the final merge, okay, we only have one cluster, like this. Okay. Of course, this code is very inefficient. The main inefficiency is here. We actually recompute again and again all Jacquard coefficients every time we want to find the maximum Jacquard similarity between two sets. So, why did I do that? Because I wanted to have a quick answer to the exercise. Of course, if you have to implement a code like that, you should rather try to mimic what I have done before at the blackboard. So you pre-compute a table of Jacquard coefficients, and then every time you merge two clusters, you merge rows and columns of that matrix in order to only keep the relevant Jacquard coefficients, only the similarities between the clusters that you are using. So this is just quick and dirty solution, just to remain within the boundaries of this lesson. Okay, so now anyway I will put this code on the web page so you can download it and play with it if you do not find the time to work with it. If you don't have the questions, I think that we can stop here and see you next Monday.
Can you scroll it down?
Oh yes.